Hey, and welcome to Unit 7, Notes 5-2. Okay, so today we're going to be talking about inclusive events, and then we're going to also talk about the difference between mutually exclusive and inclusive events. So first of all, remember, if I talk too fast, you need to pause this so you have time to write it down. First of all, for inclusive events, we're talking about events that do affect each other. So you really have to ask yourself, is this something that could happen both times? For example, if you're pulling something from a deck of cards, you could be a red card and a queen at the same time. Those things could both happen. Okay, so when that happens, we take the probability of one thing, add it to the probability of the other, then we have to subtract off the probability that it's both. The reason being is we don't want to account for something twice. Okay, so we're going to take the probability of the first thing, plus the probability of the second thing, and then we're going to subtract off the probability of both things happening. So this is going to really require us to think logically. Let's take a look at mutually exclusive versus inclusive events. So for mutually exclusive, that's what we talked about yesterday. One item cannot be both. They don't affect each other. They're two separate things. You're either a blue M&M or you're a green M&M. Okay, inclusive events is an item can be both. So if we're rolling a dice, you could be a 2 and an even number. Okay, so you have to take into account that a probability could be counted twice so that they do affect each other. Okay, let's take a look at these first ones. So let's take a look at number 1. So suppose that out of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both. Okay, so that both tells me immediately that I'm going to have some overlap. I'm going to have two different events. So first I'm going to find the probability that a student is taking Spanish. So out of 1,400 students, there's 550 taking Spanish. Okay, next I want to find the probability of someone taking biology. So out of 1,400 students, there's 700 taking biology. And last but not least, I want to subtract the probability of someone being both. So I'm going to subtract off the probability of someone being both. And the reason why we have to subtract off that both probability is that probability is either counted for in the Spanish or the biology. So we have to take into account that overlap and subtract off the extras. Okay, so then we're going to add the numerators and keep the denominator the same. Remember, when you're adding fractions, you keep the denominator the same. And then we want to add across the numerator. So we're going to take 550 plus 700 minus 400. So that's going to give us 850. Now, you have two options when you're writing probability. Either you write it as a reduced fraction or you write it as a decimal. Okay, so if we were to reduce this fraction, you're going to get 17 over 28. Now I'm going to write it as a decimal. 17 divided by 28 is going to give me about 0.607. Okay, so there's about a 61% chance that we get a student that's taking Spanish or biology. Let's take a look at this next one. Okay, there are 2,400 subscribers to an internet service provider. Of these, 1,200 own HP computers, 500 own Dell, and 100 own both HP and Dell. What is the probability the subscriber selected owns either an HP or a Dell computer? Well, here, this 2,400 subscribers, that's my total. Okay, that's my total on the bottom for all of them. That's the total number of people that are subscribing to a computer service. Okay, so let's start by finding the probability that it's an HP owner. So there's 1,200 HP owners. So we have 1,200 with an HP. Now I want to calculate the probability separately of it getting a Dell. So we only have 500 with a Dell. So we have 500 divided by 2,400. And last but not least, I actually want to subtract off the probability that it's someone with both. Okay, so we don't want to count that twice, so that's why we subtract off that both probability. And there's 100 that have both. So we're going to add across the numerator, keep the denominator the same. So the denominator is going to stay the same. And we're going to add 1,200 plus 500 minus 100. And that's going to give you 1,600. That fraction will reduce to 2/3. You could look at it this way, okay, those zeros, You could look at that fraction as 16 over 24. Well, what divides 16 and 24? 8. Okay, so you divide both the top and bottom by 8, and you get 2 over 3. And we know that the fraction 2/3 can be written as 0.67. Next, let's take a look at this bingo problem. Yeah, let's take a look at this bingo problem. So, all right, in the game of bingo, balls are numbered 1 through 75. These numbers correspond to columns on a bingo card shown in the table. A number is selected at random. What is the probability that it is a multiple of 4 or it is in the O column? So what I'm going to do right now is I'm actually just going to write out all of the multiples of 4 as I have between 1 and 75. So I'm just going to write them out. So I have 4, 8, 12, 16. I want you to write this down with me, 20, 24. So I just keep going up by 4s. That's giving me all of my multiples of 4. And there's going to be a lot of them. Keep going. My arm is getting tired. 56, and then I'm going to write 60, 64, 68, 72. So these are all of my numbers that fall under being a multiple of 4. So the next thing I want to do is I want to write out my numbers that fall under the O column. Okay, so I want to figure out my numbers that fall under the O column. Well, here is my O column. Okay, so I have the numbers 61 through 75. So let's just, for the sake of looking at this, write out all of those numbers. And 70. Last but not least, 74. Oops. 74 and 75. So I do want you writing all of these down on your worksheet, okay, because there's going to be a problem like this on your homework, and you're going to want to be able to see how to do it. Okay, so now I'm going to look at my two lists. So that's the O column. Now I'm going to look at my two lists, and I want to find ones that are overlapping. So I look, and I see that on each list I have 60. Oops, I don't. I'm sorry. I do not have 60. I have 64, 68, and 72. On all of those lists. You'll see that down here. You'll see this, this, and this. So those are on both lists. So that's going to be my both overlap. So first, let's count how many we have in each category. Okay, so this one, when you count it all up, there's 17 numbers. Okay, in that first category, there's 17 numbers. So we have 17 out of 75 total numbers. There's 75 total bingo numbers. Okay. Next, we want to figure out how many is in our O column. So we count up how many numbers there are between 61 and 75, and there's 15. So we have 15 out of 75. Last but not least, we want to subtract off that both element. So I notice in each list I highlighted 3 overlaps, so I have 3 total that are overlapping. So I'm going to add those together and subtract off the both. So I have 17 plus 15 minus 3. That's going to be 29 over 75. Okay, 29 is a prime number. We can't simplify that anymore. So last but not least, we're going to write it as a decimal. We get 0.387. So the probability of that happening is about 38.7%. Next page. So let's take a look at this one. A card is drawn from a deck of cards. What is the probability of drawing an ace or a red card? Well, first of all, when we're talking about cards, we know there's 52 total cards. So now I want to figure out first the probability of getting an ace. So the probability of getting an ace. Well, I know there's 4 aces. There's ace of spades, ace of clubs, ace of hearts, ace of diamond. So the probability of getting an ace is 4 out of 52. Next, I want to find the probability of getting a red card. Okay, so red cards are going to be my hearts and my diamonds. So there's 13 hearts, 13 diamonds. There's 26 red cards in the deck. Okay, so good. I've calculated my probability so far. But next I have to ask myself, okay, could a card be a red card and a 2? And the answer, or and an ace? And the answer is yeah, it can. You have the ace of hearts and the ace of diamonds. So that means we have the ace of hearts and the ace of diamonds, which is the same as being a red card. So we have to subtract off the fact that there's 2 out of 52 that are going to overlap. Okay, so you add 4 plus 26 minus 2, you get 28 out of 52. Both of those numbers are divisible by 2, and you get 7 out of 13. 7 divided by 13 is 0.538. Okay, now I'm going to get this one set up for you, and then I just want you guys to finish it up yourselves. There are 100 students that participate in spring sports. So first thing I know is that my total is going to be 100. Okay, there's 15 students participating in track, 14 participating in softball, and 12 that participate in both track and softball. So that both right here tells me I'm going to have to minus at some point. What is the probability of getting a student that participates in track or softball? Okay, so first of all, you want to find the probability that they participate in track. Okay, so something out of 100. Then you want to find the probability that they participate in softball, so something out of 100. And last but not least, the probability, you want to subtract off the probability of it being both, someone who's participating in both. Okay, next, I'm going to have you look at number 6 on your own. Just for reference, there are 13 clubs in a deck, and there's 4 10s in a deck. So you can write out those probabilities pretty easy, but then you need to ask yourself, can a card be a 10 and a club? If it can be both, then you're going to have to subtract something off. Last but not least, let's look at this. We want to look and see if an event is mutually exclusive or inclusive. So I'm just going to pull a couple of these out, then I'm going to have you also try some on your own. So taking a look at this guy, drawing a heart or a diamond from a standard deck of cards. So you're drawing a heart or a diamond. Can a card be a heart and a diamond at the same time? Not so much. It can't be a heart and a diamond at the same time. So we have here a mutually exclusive event. Next, let's take a look at this. Look at Humpty Dumpty, isn't he cute? All right, number 2, drawing an ace or a spade. So now we're still talking about cards. Okay, could a card be an ace and a spade? Yeah, it can, the ace of spades. So because it can be both, I have an inclusive event. Okay, next. The probability of rolling a 5 or a number greater than 3. Okay, so I have a dice, rolling a 5. Okay, that's only one way that can happen. Rolling a number greater than 3. Well, numbers greater than 3 are 4, 5, and 6. Uh-oh. Okay, it's possible that both of those things could happen. So that makes it an inclusive event. I want you guys to try this one on your own. Is it mutually exclusive or is it inclusive? Okay, so ask yourself that question. And then once you have a completed note sheet, go ahead and show it to Ms. Humbert and you can get started on your homework. Thanks for listening. You guys are awesome.